everyone. Welcome. We're so excited to have you here today. My name is Molly Larkin. I'm with Fourth Brain, and we're very excited to have this event today all about TimeGPT. We have Camilo Santo. He's a longtime Fourth Brain instructor and a machine learning engineer at Bearing.AI. And we also have Azul Garza Ramírez with us, who is the CTO and co-founder of Nixla and one of the creators of TimeGPT. I'm going to hand it over to both of you. Throughout this event, please feel free to put any questions you have in that chat over on the right-hand side. We will get to them maybe during the event, maybe afterwards. But please put any chats you have in there, any questions, and we will get to them. Camilo and Azul, please feel free to add to your intros, anything about you that you'd like to share, and then we can get started.
Yes, so thanks a lot, Molly, for setting all of these up. My name is Camilo Santo. I'm a machine learning engineer at Bearing. I'm like tech lead manager of the core tech team at Bearing.AI. And we're trying to bring the AI to the maritime industry. And it's been a ride with time series. We've been doing a lot of stuff with large maritime models, and yeah, I'm pretty glad to be here and to share the stage with Azul. So yeah.
Okay. Thank you, Camilo. Thank you, Molly. I'm Azul. I'm CTO and co-founder of Nixla. We developed TimeGPT, one of the things that we'll be talking about today. Thank you very much for having me. I'm really excited.
Okay, thanks. So yeah, we'll be seeing a little bit TimeGPT and how it stacks to other state-of-the-art time series analysis. So in this case, yeah, a little bit about my background. I've done a bunch of time series analysis, from ARIMA to GARMA, using Fisher scoring, and also on the physical side, using neural networks to do time series analysis. And now, with all these generative AI boom, so we're starting to see this come out in all sort of domains. So we're gonna go, for example, this is the content of the talk. I'm gonna give a brief intro, then we're gonna talk about deep learning models for time series analysis. So Azul is gonna start giving an overview of TimeGPT, but she's also worked on this NHITS model. She's the main author of both TimeGPT and NHITS. So yeah, that's a great contribution. We're also going to talk about NBeats, which is the spiritual predecessor of NHITS, and finally also some temporal fusion transformer. So these are transformer-based models. This is multi-layer perception models, and we're going to go over both. I'm going to give a brief overview of the large maritime models we've been doing at Bearing.AI. And finally, we're going to do a very short coding session, both in Darts and Nixla. So go over that. Okay, let me give a brief intro on time series. So what's basically a time series? A time series is just a sequence of data points captured in a regular basis, on a regular time basis. So ideally, this is very different from what we've done on a transversal sense. We have some models that we only interested on predicting for a single time point, a different amount of variables. But in the time series, we're mostly focused on the time dependence and how a future value depends on the previous values. So that's the idea of time series, trying to capture that time dependence. And when we have this time series analysis, we're going to have a specific frequency. So this frequency is how often do I get data. So it could be on a monthly basis, on a weekly basis, on a daily basis. And most of the time, the classical time series analysis, we split this into two components. So we can also see this when we do time series analysis with profit or with classical algorithms. And one of them is like the trend. This is like basically the long-term time dependence, the long-term behavior of the time series. And then we also have like some seasonality. So this seasonality is like the more finer grain like variations of the time series. For example, here there's a very used like Kaggle and data set that's very popular for time series analysis. And we can see there's a seasonal component, like a yearly component, but it's also increasing over time. So most of the time we split those like in those two components, but we can also have like different seasonalities. So we're gonna see a bunch of examples. For example, the stock market. The stock market can have like yearly seasonalities, can also have like weekly seasonalities, and we can have all of those combined. Or the energy market, so we can expect like the energy might change price weekly on a weekly basis, but also on a daily basis, because like the behavior of the energy market is going to change both weekly and maybe hourly. So that's some basic examples of time series. And in the coding exercise, we're going to look at another time series, a pretty interesting time series, at least in my domain. It's trying to predict vessel positions. So here we see like what's a specific vessel's latitude and longitude over time, and we're going to try to predict it like in a horizon of 12 hours. So this is like another sort of time series. So like we've done we've come a long way. We used to do like ARIMA and GARCH. So ARIMA is basically autoregressive models, integrated and moving averages. So this like basically says that the value of a future time series is going to depend on the previous values. So this is the autoregressive part, and on the like errors or the residuals of previous time steps. That's the moving average. And we also have like this autoregressive with is conditional heteroscedasticity. So these are very good models. They're still very good. So if we have like a very small data set, they're going to be we're going to have very high accuracy. The issue is that we're going to have to do some feature engineering to do those, because we're going to have to do a bunch of tests with different time lags. There's some engineering there. So they're still very good. They have high accuracy, but we need to do some feature engineering. And then we also have like this plug and place approaches like Profit and DeepAR. And they work also very, very, very good. So Profit from Facebook, DeepAR is from AWS. And you can use them sort of like in a plug and play way to predict your time series. Let me just go over. And in all of this, we're gonna there's a question in the chat, like what does autoregressive entail? Like on the autoregressive side, we're gonna predict like a value in the future is gonna depend on certain time steps in the past. So we're gonna have a bunch of feature weights, and we're gonna do like an additive model of the previous time steps. So for ARIMA models, we actually need like this feature engineering actually requires to do some autocorrelations and see what's the time steps in the past that are more important to predict like the future. So it's a little bit time consuming doing that feature engineering. That's why we're gonna try to like automate everything with deep learning models. But for all these, we're gonna use this sort of terminology. So we're gonna have a target series. This is what we're actually trying to forecast. So this diagram comes from the DARTS website. So this target series is what we're trying to forecast. So in our specific case, in the coding session at the end, this can be the latitude and longitude of a vessel. We can also have past covariates. So these are measurements that we know in the past, but we're not going to know in the future. So for example, in the past, we know the speed of the vessel, or we know how much loaded it was, but in the future, we might not know those variables. But this is actually going to help us predict this target series. And then we're also going to have like some future covariates. So this is some variables that in the future, we're going to know their values. So this could be like holidays. We can know like the calendar. We know what year it is. Like we know when we have weekends, when we have weekdays. We can get weather forecasts. So this is like not very like accurate, but we can also get weather forecasts. And we can also like for a specific vessel, we can know like what's the destination port, or like what's the fuel it consumes, like what it has on board. Like on a specific voyage, we know how loaded it is. So this is like the terminology we're going to use for time series analysis. And finally, we want to talk about like how to do a ideal data split to test all of this. So for time series analysis, we want to test the model as close as we're going to use it in production. So what we're going to do in production is we're going to train the model today, and we're going to use it to test, like to predict the location of a vessel tomorrow. We're going to use it like in the future. So when we are talking about time series, what we want to do is we want to split the time series like into training and test by time. So we want to make sure that none of the testing data leaks into the training data. So we want to split like in a specific date. We want to split the data there and make sure that that doesn't get into the training set. So this is like, for example, how scikit-learn does it. So this is how scikit-learn does cross-validation when you have time series. So it starts like moving the split in time. Yeah, so sort of like the training sets growing for each fold of the cross-validation. So this is ideally what we want to do in time series analysis. And now we are going to go to the neural network models. So Azul, she's the main author of TimeGPT. She already presented herself. Like what I said about my background, I've been using like time series like a bunch of my life. I've been implementing them, but actually Azul has been like designing and creating new methods, and that's like just another level. So I'm gonna leave you for Azul for a while.
Thank you so much, Camilo. So basically we are Nixla. We are a time series research and deployment company, and basically, as Camilo mentioned, we designed different neural networks models, including the NHITS model and now the TimeGPT model. But not just that, we started as an open source company in the time series forecasting field, and we have several different libraries. And let me show you our ecosystem. So basically, we have different libraries for different use cases. For example, if you want to test classical statistical models, for example, ARIMA, as Camilo mentioned, and so on, you can start playing around with Stats Forecast. And Stats Forecast basically contains a lot of different statistical models. For example, we have AutoRIMA, AutoETS, AutoDIDA, and also we have models that handle multiple seasonalities like MSTL, the GARCH and ARCH implementation, and also baseline models, for example, historic average, naive, and so on. And the main thing about Stats Forecast is that we implemented the models from scratch, in the sense that some other libraries wrapped some other implementations, but we used NumPy to make the models faster. And also we have a lot of different experiments showing that our implementations have the best performance among other competitors. For example, if we compare ARIMA against Prophet, we can see that our implementation is a lot faster and also is more accurate. So Stats Forecast is a good starting point to produce forecast. Also, we have more complicated or newer forecasting methods. For example, we have ML forecast. If you want to use sklearn, you can use our implementation. The main thing with machine learning models in time series forecasting is that you need to perform feature engineering, right? Because at the end of the day, you need regressors to forecast the future values of the target time series. In some cases, that feature engineering part can be really expensive in terms of computational complexity. So ML forecast is highly optimized to perform that feature engineering faster. And also we have neural forecasting methods in our neural forecast library, which includes our NHITS model. And we also have a lot of different libraries to perform time series analysis. For example, utils forecast, core forecast, that allows you to include several steps of the forecasting pipeline to deploy it into production. And specifically with TimeGPT, let me show now our paper. Let me see how I can. Just a moment. Nice. So basically, we released TimeGPT. This TimeGPT model is the first foundational model for time series forecasting, in the sense that we scraped a lot of different time series in the world. In fact, we believe that we have the most comprehensive data set of time series in the world. And it includes a lot of different sources, for example, retail, finance, electricity, and we used a transformer architecture. Let me show you this diagram. Basically, we trained a transformer-based architecture on that data set, and we saw that with zero-shot inference, TimeGPT has a really good performance. And we compared the performance of TimeGPT against a lot of different models, for example, historic average, seasonal naive, statistical models, and also LiveGBM, which is a machine learning model, but we included some neural forecasting methods. And we compared the performance against different frequencies, in this case, monthly, weekly, daily, and hourly. And for zero-shot inference, this means that we didn't train TimeGPT in these data sets. We saw that TimeGPT has the best performance across the data sets. And we are really excited about these results, because at the end of the day, we were able to train a large time model, and then we deployed it in an API, and then everyone can start playing around with this model. And yeah, just for answering the question, yes, it is an API. Let me show you how it works. We have this Python SDK, which allows you to interact with the TimeGPT API. And basically, the TimeGPT API works like this. Basically, you need to import Nixla TS, which is the library that allows you to interact with the API. You need to authenticate yourself with a token that you can generate. In a moment, I will show you how you can generate the token. And then you can start forecasting using TimeGPT, just calling the forecast method. And this is really, really interesting, because at the end of the day, you don't really need a dedicated team of machine learning engineers, data scientists to deploy a forecasting model into production. You just need to call our API, and you will have all the infrastructure problems and all the science problems solved with this TimeGPT. If you want to try TimeGPT by yourself, you just have to go to get token page, and you will get a token, an API key, and then you can start playing around with TimeGPT. In terms of the features that we are offering right now, I think that yeah, you just have to go to get token, and you will have access to a page like this, and then you can generate a token here. And once you have a token, you just have to pass it to the Python SDK. But also, if you don't work with Python, you can still using TimeGPT through our REST API. So basically, the REST API allows you to use any programming language. For example, JavaScript. In this case, for example, you can see how you can use TimeGPT using Node, but also Ruby or PHP. And C++, among other programming languages. In terms of the features that we have right now, basically you can find them here. Here is a small quick start. But for example, if you want to perform anomaly detection, you can also use TimeGPT. Basically, you just need to call our detect anomalies method. And of course, you can use also exogenous variables. For example, in this case, we have different time series with different exogenous variables. In this case, for example, we also have calendar variables, and you can use them as an external regressors. Also, you can include prediction intervals, because in forecasting, we are not only interested in forecasting the mean value of the time series, but we are also interested in measuring the deviation of those forecasts, or to have a better understanding of the uncertainty associated to those forecasts. So basically, you can include the level argument on the endpoints here, for example, and you will have not just the mean forecasted value, but you will have a range that allows you to measure the uncertainty associated to those forecasts. And I think there is questions. Let me share different resources. Yeah, I think I cannot write in the chat, but I will be sharing with Camilo and Molly some resources. And just to finish this part, we also have the cross-validation method, something that Camilo mentioned in the introduction. And this is really important, because at the end of the day, to validate the forecasting accuracy of TimeGPT and some other models, you need to perform cross-validation. And in some cases, this is really difficult, because at the end of the day, you have to iterate across the time series to have the expected performance of the methods you are using. But with TimeGPT, you can also do that in an efficient manner. You just have to call the cross-validation method, and you will have forecast for the different windows you want to compare. Here, for example, we are generating TimeGPT is generating forecast for different windows of the time series. And once you have them, you can calculate the accuracy or performance of the model to see if in your use case TimeGPT improves the forecasting. And of course, you can create those forecasts also in terms of prediction intervals to quantify the uncertainty, and so on. So that's basically the idea behind TimeGPT. I will stop here to give Camilo some time to deep dive in the other topics of the talk. But I will send some material regarding TimeGPT. And that would be all from my side. Thank you so much.
Thanks a lot, Azul. Thanks a lot for taking your time and showing us all of these, and mainly for creating all of these. So yeah, it's a great contribution to the time series analysis. Okay, so let me just keep talking about the other models. So we're gonna, in the coding session, we're gonna pit TimeGPT against this ones, and I'm gonna see how it goes. So basically, First is the NBEATS model. So NBEATS stands for Neural Basis Expansion Analysis for Interpretable Time Series. So it's quite a name. That's why it's called NBEATS. And basically what we do is we're gonna have like a multi-layer perceptron neural network that's gonna have like a look back period. And then it's gonna have a forecast period. So we're gonna look at the back of at the past, and we're gonna try to predict using a bunch of these stacks. So we're gonna have a bunch of stacks, and basically each stack is gonna like contribute to the prediction, and each stack is a collection of blocks. So each block is some fully connected layers. So here we have like 4 fully connected layers, and we are gonna have like 2 outputs for each block. So we're gonna have a backcast and a forecast. Why do we do that? So why do we need like this backcast? This backcast is trying to predict like the input it receives, and it's basically like trying to remove all the signal it can explain. And here we have sort of a residual connection, like from the beginning to the end of the block. So this backcast is trying to model this input and trying to remove all the signal it was already able to analyze. And then the next block is gonna work with the remaining signal, and we're gonna do that k times. So this is this backcast, and the forecast is the one that's actually gonna do the prediction. So this is the actual target I'm trying to predict. So basically, this NBEATS, it's not like the neural networks are basically trying to get some like coefficient of an expansion, like of a functional expansion. We're gonna see why, but yeah, like up until now, it doesn't seem interpretable. But yeah, it's just a bunch of neural networks stitched together trying to forecast a time series. And what makes it interpretable is changing the infrastructure a little bit. So instead of having like M stacks, we're going to have just 2 stacks, one stack to predict the trend and another stack to predict the seasonality. So this is what we call like the interpretable architecture. So this one's going to give us like a long, like a single trend, and the other one's going to give us another fine-grained prediction. So how do we do this? Like it's not just like reducing it to 2 stacks. So what we do is for the trend stack, we're gonna change like the functions of this series expansion to actually be like a power series. And for the seasonality, like why do we pick a power series? Because it's actually like monotonically increasing. And for the seasonality, what we need is a bunch of functions that have like a harmonic, that they're periodic. So they're going to be repeating over time. So here for the seasonality, we're going to pick like the Fourier series. So this is like what we get at the end. So one of the stacks, we're going to predict this coefficient, but it's going to be a power series in time. So this is like the current time step to an exponent. And on the seasonality, like we're predicting this coefficient, but then we're gonna have like this repeating functions, the cosine and the sine function. So that's why it's sort of interpretable, because we're gonna split it into trend and seasonality. And then it comes and hits. It tries to solve the same problem, but it's gonna be way faster. Like the issue with the NBEATS is a little bit slower, and hits solves it in a very surprising way. So we're still gonna have a bunch of stacks, each stack composed of a bunch of blocks. But the main like breakthrough here is that we're gonna have like a max pooling layer on each stack, and each max pooling layer is gonna have like a different size. So what this does is that each stack's gonna look at a different time series. We're gonna pool like the whole time series, but with different sizes. So if we have a big kernel size, we're gonna look more into the trend of the time series. And if we have a smaller kernel size, we're gonna look more into the seasonality. And not only that, like if we have a big kernel size, this is going to reduce like the time complexity of the problem. We only, like here, we're only looking at 3 data points. So this is going to be more efficient. And at the end, this other, like, we're going to do like an interpolation. So we're going to take like this time series back to the original frequency. So this actually works pretty good. Like this is the state-of-the-art model. And it's pretty fast because this max pooling layer is going to reduce the complexity. So that's like the main advantage of NHITS, but it's sort of like the same infrastructure we have in NBITS. And finally, yeah, we're going to have like this temporal fusion transformer. So this is a bunch of data. We're going to go like over each component in some detail. So first, we see that this is like it's going to be like a multi-headed tension model. So this is like the core of the temporal fusion transformer. It's going to be this transformer model, which is multi-headed tension. And we know that multi-headed tension is very interpretable because we have like the energy, we have the context vector, and we know what we are attending to. So this is going to give us like a layer of interpretability to our model. And then the main issue, like with TFT, is that it's a little bit slow because it has an LSTM encoder and decoder. And we know that, recurrent neural networks could be a little bit slow to train due to their recurrent nature. They are sequential in nature, so they're a little bit slow. So what we're going to have is we're going to have like the past inputs. This is what we call like the past covariates. We're going to have some static metadata, and then we're going to have like future covariates. And all of these inputs here are going to go through a variable selection network. So this network is basically another neural network that's going to give me a weight for each input. So this network at the right is actually telling me what variables are more important when I'm going to predict like my target series. So this is very interpretable. This is going to give us like a feature importance. Then we have the LSTM encoders. We have a bunch of like this gated residual networks. So we know that if the variable is not very important, we're just going to skip the network. This is like this residual connection. And that's why we have this gate. Like if the variable is not going to contribute a lot, we're just going to skip it. And finally, after the multi-headed tension, we're going to have like a dense prediction, and we're going to do quantile forecast. So as Azul was saying in the TimeGPT, we not only have like the mean prediction, we also have like some intervals. So here we can also have like some confidence intervals for our predictions, like the 10%, 90% confidence interval. So this is the TFT architecture, and we're gonna compare these 3 architectures against TimeGPT in the coding session. And finally, we have TimeGPT, as we already explained, like all these TimeGPT, it's a fully transformer model, and we're trying to get this forecast. And it was trained with a whole bunch of different domains from web traffic, IoT, transport, healthcare, and it captures different frequencies, and it's basically just an API. You send the data, and you get like prediction like magically. So we're also going to use this TimeGPT. And this is the plot Azul showed. So we know TimeGPT is among the 3 best models, along with TFT and NHITS, which is what we're going to show in the coding session. Okay, so finally, before we start the coding session, I also wanted to show something Bearing.AI is currently doing, which is called the large maritime model. So we're using all this generative AI technology that's been developed to predict the whole global fleet. So first, what do we currently do at Bearing? So we do like automated emission tracking. So we track the emissions of different vessels, and we use like deep learning performance model to actually be able to simulate a whole bunch of scenarios. And these scenarios could lead to a fleet-wide optimization and like proactive recommendations for fleet operators. But yeah, basically the large maritime model, we have 70,000 vessels in the global fleet. Each vessel has AAS data. We're going to go over AAS data in the coding session. We're going to use like a single vessel for the coding session, but this AAS data just tells where the vessel is in each point in time. We're also going to have like historical weather patterns, market conditions, and we're going to feed all of these into a large maritime model. And we can use it for a whole bunch of stuff. We can do global fleet patterns, so we can know like what vessels are going to what parts of the globe at each moment. We can do voyage planning. We can do like smart routing, like weather routing. We can do like fleet allocation, so we can know where the vessels need to be in each point in time. So this is just like like what's coming up in a couple of months in this case. Okay, so I'm gonna answer a couple of questions before we go to the coding session. On TimeGPT, it can be fine-tuned. We're gonna see how we can fine-tune TimeGPT in a bit. It's still an API endpoint. You send like a history of data, and it actually like fine-tunes on that history of data and then predicts like the next horizon of data. Okay. Let me see what other questions we have. Okay, another question from Surjani. Is it for univariate and multivariate? So that's a great question. Most of them are univariate, but for example, TimeGPT also receives a exogenous variable. But yeah, we only have like one target variable at the moment. And for TFT, like we can also receive multivariate inputs. But yeah, like it's basically on the coding session, we're going to do it on the univariate case, but we can also receive multivariate inputs. Let me just see some. Let me go over more questions. Another question from Surjani. TimeGPT at the moment cannot be downloaded. It's an API that's exposed. But yeah, maybe in the future, like Nixla is really advocating for open source software and actually being able to run everything like locally. So at the moment, it's an API. Maybe in the future, it could be downloaded and run locally. Okay, I think we can move forward to the coding session. So we're going to run all of these on Google Colab, and these resources are going to be available like tomorrow, and you can download it and run it like also locally on Google Colab, however you want. And this is like what we're going to do. This is like a brief overview. We're going to install some dependencies. We're going to use our like Google Drive storage. So we're going to mount this Google Drive. There's going to be some imports for neural forecast and darts. Then we're going to do some exploratory data analysis. So this involves doing like some min-max scaling to have like a better forecast, some great circle distance computations. And then we're going to go with the darts modeling. We're going to go with n-beats and hits and temporal fusion transformer. And then we're going to see how we can do all of that in neural forecast. And it's going to be like 3 lines of code, and it's going to optimize all the parameters we need. And finally, we're going to go with TimeGPT, where we're going to do like the anomaly detection, historical forecast. We're going to see how we can get like the prediction intervals, and then finally some fine tuning. Okay, so let's get to it. Let me just connect to an environment. So here I'm going to start by installing some dependencies. This base map is just a library to plot like in a map, like in a geographical map. So we're going to see it in a bit working. Neural forecast from Nixla, darts. This is a Python library to do time series analysis. And then Nixla TS for TimeGPT. So this is going to install all the required dependencies that we have. We give it a bit of time. Okay, there's another question in the chat. So at the moment, the large maritime model, it's under development. We're going to use some similar infrastructure to TimeGPT. So that's going to be like a pre-trained transformer. But yeah, it's still under development. So it's not like there's some the information available online, but yeah, the infrastructure and all that's still under development. Okay, I'm gonna mount the Google Drive where I have the data stored. And then I'm gonna do like a whole bunch of imports. So we're gonna use basemap to plot like in the globe. We're gonna use matplotlib to plot some other stuff. We're gonna use GeoPy to compute the distance. So we know that the actual distance between 2 points in a globe, it's actually like a great circle path. We're gonna use Ray to do some like distributed computing, like for Nixla neural forecast, and Pandas and NumPy and Torch to train some stuff. Then the neural forecast, we're gonna use auto and hits, auto and bits, and auto TFT. So this is gonna run over a grid of variables and get the best combination of variables for the n hits architecture. And we're gonna do the same for n bits and TFT. We're gonna see that in a bit. And finally, we're gonna use darts. So we're also gonna use darts and beats and hits and TFT model. Wait for it to import everything. Okay, so in this coding session, we're gonna work with something called AAS data, which stands for Automatic Identification System. And it's basically data that every vessel reports, both satellite or terrestrially. So yeah, each vessel needs to have like an AAS transceiver, and they send their location on real time. And this is mostly collected by the National Oceanic and Atmospheric Administration here in the US. And we have data from 2009. We're basically using data from 2021, 2022, and 2023 data. And we're going to pick a specific vessel, which is this one. I'm going to show you how to do that. And the data basically has like the UTC, which is the universal time, the latitude of the vessel, the longitude of the vessel, and the IMO. The IMO is basically the vessel's ID. And I already have that on Google Drive. I can share it. And this is comprised like of 24,000 measurements. Let me just show a little bit of the data. So yeah, it has IMO, it has UTC, it has latitude, and it has longitude. So yeah, this is basically like a time series. And what we're gonna do first is resample it to 1 hour. So I'm gonna resample everything to 1 hour. And every time I have a missing measurement, I'm just gonna forward fill it. So basically we have missing measurements because yeah, maybe the vessel was turned off, but yeah, it's still on the same place. So that's why we are gonna forward fill. Here we need to rescale it. So our latitude and longitude. So the latitude has a range between -90 and 90, but we need to rescale it. While the longitude has a range between -180 and 180, we also need to rescale it. So we could do the like a latitude and longitude rescaling. Here we're gonna use a max-min rescaling, and we're gonna see how that works. So we see this is the latitude of the vessel in each point in time. This is the longitude of the vessel, and after resampling, after rescaling, it's in the 0-1 scale. So here's the latitude and longitude both, for this specific vessel. And we can actually plot it in a map. So here we're using base map, and the red lines denote like where it's been like through the US. So this is like the data we're gonna handle in this coding session. And here we're gonna use a horizon of 12 hours. So what we're gonna try to predict, it's what's the location in the next 12 hours for a vessel. So to give a comparison, like the state-of-the-art models, have like an accuracy of around 10 nautical miles after 12 hours. So a nautical mile is very close to a mile. So that's like the baseline we want to achieve. We want to be less than 10 nautical miles in accuracy after 12 hours. And here we're going to split the data. So we're going to pick let me just show the size of the data. We're going to pick the first 24,060 measurements as training, the last 12 as test. Ideally, we would want to do like cross-validation here and then use this as a test. So this is what we're going to do. So, and we're going to measure the Haversine distance. However, the Haversine distance, we need to unscale the data. So this is just like a helper function to unscale the data from that min-max scaling. And we can go forward with the darts model. So here it's a very helpful encoder function. So this will allow us to have like the future covariates we talked about. These are the covariates we have in darts. So we know like what month we're actually at, what hour, what day of the week. What year we are at. So this is like the future covariates we're going to have. And for darts specifically, we need the data in a time series format. So we're going to use this time series. We're going to use this from data frame to get the data, both latitude and longitude, into that format that darts accepts. And each of the models, we're going to train it for 100 epochs. We're going to chunk it by like 24-hour segments, so day segments. And the output is going to be like every 12 hours. And we're going to have some early stopping to make sure like if it's not going to overfit. So let me just go over a little bit over the NBeats infrastructure again. So in darts, we can define all of these hyperparameters for the architecture. We can define if it's the generic architecture we have here or if it's the interpretable architecture we talked about. We can define the number of stacks. By default, it's going to have 30 stacks. We can define the number of blocks in each stack. By default, it's going to have 1. And the number of layers of these fully connected layer, it's going to be 4 layers. And each layer is going to have 256 dimension. So this is a bunch of other hyperparameters, for example, the polynomial trend that we want in the interpretable architecture. So we're going to run it this way. And then we have n hits. Once again, we have all the, we can determine the number of stacks, the number of blocks, the number of layers in each block, and the layer width of each block. And finally, we could also define the kernel size. So we could define like each block, what's the kernel size each block is going to have. Finally, for TFT, we're going to have like the hidden size, how many LSTM layers I'm going to have, how many attention heads I'm going to have in the temporal fusion decoder. We can have all of that. And this is the code we use to train the actual models. So this takes some time to train. So here I'm just fitting the models, I'm saving them. So I'm not going to fit them again. I'm just going to load them from my Google Drive. So I already have them trained. And this is how we would do predictions. So once we have the model, we just need to run predict, and we're going to get some predictions for each time series. Let me just show you what we get. For example, so we have predictions for latitude. Let me just show. These are the predictions for the latitude. These are the predictions for the longitude. We're going to see them plotted in a bit. So this is some accuracy measurements. So for example, this TFT model didn't perform that well. We have like a 35 nautical mile error after 12 hours. But however, the N hits and the N bits, like for example, the N hits has a 6 nautical mile error after 12 hours. The N bits has a 11 nautical mile error after 12 hours. And that's pretty close to the state of the art. And this is what they actually predicted. So here we have the latitude and longitude. On black, we have the actual values, the actual position of the vessel. So here in purple, we have the N hits prediction. In blue, we have the TFT prediction. So after some time, it actually goes pretty rogue. And the N bits prediction, that it's also like a little bit closer. But yeah, as expected, we see that the N hits is actually closer to the black line. So this is how it would look in the actual map. In this case, the test, the actual voyage is the red line, and N hits is pretty close to that red line. And here we can actually see like the distance metric. So we see that N hits is consistently under 10 nautical miles error, and the other ones are like after 6 hours they go over 10 nautical miles error. We can improve this. Like we're gonna use neural forecast to actually improve, like we can improve these predictions for the other models. So this is the darts section. This is how you train the TFT and hits and bits using darts. We're gonna see how we can do that using neural forecast package, which is gonna automate a bunch of these choices we have. So for the neural forecast models, we need to define this configuration. So this is we're gonna try a whole bunch of different combinations for this hyperparameters, like the input size, the step size, the learning rate, the scalar, the max steps, and we're gonna loop through a bunch of these, and we're gonna pick the best. The same for the N hits. So for the N hits, for example, we can loop through different combinations of the kernel size, of the frequency downsampling, of the interpolation. And for the TFT, we also have like the hidden size. We're gonna pick different hidden size, different architectures. And here is how, like it's gonna produce like a neural forecast object with the 3 models. And this is how we would train those models. So as with darts, we already have this pre-trained. We're not gonna train it here because it's very time consuming. We're just gonna load the models, but this is like what we need to train. And in this case, like with neural forecast, we don't need to have a time series object. We just need like this data frames. Let me just show you, like we just need like this sort of data frames where we have the type of the variable I'm trying to predict, so the latitude and the longitude, the time I'm trying to predict, and the actual value. So here I don't need to create like all these time series objects that we had to create in darts. And here I'm gonna load the pre-trained model. So I have the N beats and N hits and the TFT. And I'm gonna do the predictions for each of these models. So this is how we would predict the different models. It's just predict, and I'm gonna give it like the training series, and it's gonna predict the test series. And let me just plot those predictions. So they're like underestimating the latitude a little bit. here are the three models. We have the M beats in blue and hits in pink, and TFT in green. They're very similar values, and this is the actual value of the vessel. Let me just remove one of these. Black is the actual location of the vessel. Let me do the same for the longitude, and we can plot them. Okay, so they're very close. I think it's just a 12-hour interval, so it's not very easy to see, but they're at least closer than what we have. And let's plot, this is the distance. So we see that the distance is very, very close to 10 nautical miles after 12 hours. Let me just compare this against other models, against the ARTS models. Okay, so here we're gonna have like the TFT and hits and N beats, like in lowercase. These are the darts models. So the black, the pink, and the blue. These are the darts models, and the other three models, the neural forecast models, are this, this blue, this green, and this orange models here. So we see that N hits from darts still better than the other ones. So this is like the best one, but the neural forecasts are not far off. So here we have the other ones. Okay, and it actually improved like the TFT and the N bits models that we had from darts. This actually considerably improved. Now, finally, let's go with TimeGPT. That's why everyone's here. Let's see how it works, how we can use it. So I'm gonna create like this TimeGPT object. So here we're gonna use like a my API key. So in Colab, you can save like secrets here and use them in the code. So I'm gonna use this my API key to create a TimeGPT model. And first, we're gonna see how we can detect anomalies. So this is my time series, and I'm gonna predict with hourly frequency. I need to tell TimeGPT that it has hourly frequencies. And here I'm running I'm calling TimeGPT. So this package, this Nixtla.ts package, actually is just like a Python wrapper that has all the API calls that needs to be used in TimeGPT. So here it called TimeGPT, and it predicted a bunch of anomalies. So here we have like the anomalies it found in latitude. So for example, this like weird peak here was detected as an anomaly, but it also detected a whole bunch. And I'm plotting here the predicted value that TimeGPT would have given. And this is like the anomalies on the longitude. So we can use it to actually predict, like to detect anomalies. We can also use it to do a historical forecast. So we can forecast the whole time series. So here I'm running TimeGPT to forecast the history. This is 24,000 data points, and I'm calling TimeGPT to predict all those 24,000 data points. And we can see that it's actually very close to the real value. So the blue is the actual AS value, the black is the TimeGPT prediction, and we see it follows very close to the trend. And this is for longitude. So we can do this historical predictions. And as Azul showed, we can also predict at different levels. So yeah, most of the time we don't need like a specific, like a single prediction. We want to know some interval, like some confidence interval. So for example, the 80% confidence interval or the 90% confidence interval. So I can pass this level parameter here, and it's gonna return like those confidence intervals. So here's the actual forecast in red, the 80% confidence interval and the 90% confidence interval compared against the actual latitude and longitude, we see at least it falls in like the in the intervals, in the defined intervals. And finally, we can also fine-tune TimeGPT. So here I'm passing the number of fine-tuning steps. So I'm only gonna use like 10 fine-tune steps, so it's gonna be a little bit faster. And I'm gonna plot the results. We see that after fine-tuning, the forecast matches closer to what we had before fine-tuning. So it's actually working. The fine-tuning is actually like doing what it's supposed to do. And now we're gonna see how all of these compares against the other methods we had. So for example, here, this black line, this low black line is TimeGPT after fine-tuning. This red line is TimeGPT without fine-tuning. So it's really comparable to the other methods. I just want to mention that it's only fine-tuned for 10 time steps, and this is just a single vessel. So yeah, ideally, we would need to run this like with a more significant size of vessels, maybe the global fleet, and see how it turns out. But yeah, we see that this is without having to do any training. This is just like the generative pre-trained model already has very, very good accuracy to predict this vessel positions after 12 hours. Okay, this was all we had for the coding session. Maybe we could answer some more questions. I'm sorry, Molly. I think you're muted, Molly.
Sorry about that. Thank you. Can you hear me now?
Yeah.
Great. Thank you so much. That was really great. We do have quite a few questions queued up, so we'll do our best to get to as many of them as we can. If we can't, we will do our best to answer them and send out answers later. Azul did have to drop off, but I'll be sending some questions to her later that you've asked about TimeGPT specific things, and we'll try to get those answers out via email tomorrow. That email will go to anybody who registered on our website for this event. All right, great. So let me, I'm going to jump in, Camilo, with one specific question, and then we'll go a little bit more generic. So Amit has asked a few questions about like the maritime data specifically, you know, latitude and longitude are very obviously closely related. Also, like the captain is involved. And so, you know, it's not just random. So I'm sort of combining a couple of questions there. But do you want to just kind of elaborate a little bit on the type of data that you work with and kind of how this all works together?
Yeah, basically. So yeah, Amit has like very good questions. Latitude and longitude, definitely they're not independent. They're depending on each other. So that's a great insight you had there. So yeah, basically what we could do is when we try to predict, we could predict both like in a single model, and we can capture those interdependencies. Or let's say we can have like a latitude model that has the longitude as a covariate, and vice versa, having a longitude model that has a latitude as a covariate. So yeah, definitely they're gonna depend on each other. So yeah, if we treat them like independently, as we did in the coding session, which was like a toy model, yeah, if we treat them independently, it's not going to be as good as if we consider their interdependencies. So yeah, that's a great eye there.
Great. Okay, great. I'm going to start a couple questions about sharing the paper that Azul talked about, sharing this notebook. Camila, would you be able to share this notebook later on?
Yeah, definitely.
Yep. Well, yeah. So we'll definitely share the papers and the resources that Azul mentioned earlier. The notebook, we'll get those all out in the comments and via email. So you all can wait for that. There's a few questions about anomalies. So TimeGPT seems to be doing a lot of that. Can TimeGPT explain the anomalies? Can you elaborate on that at all?
Okay, so yeah, that's a very good question. I'm not sure if they can explain the anomalies. In this case, like what we could do is we can establish different confidence intervals and see like which points fall outside those confidence intervals. So for example, for the anomaly detection, we pick like, for example, 99% confidence interval. And if it falls outside that 99% confidence interval, that would be considered an anomaly. In this case, for example, specifically for AAS data, GPS data is very noisy. So that's why it flagged a bunch of points as anomalies. And yeah, it could be that maybe like from that GPS noise, we couldn't like physically be able to travel from one point to another, because it would mean like the vessel would need like extraordinary speed to go from one point to another. So yeah, TimeGPT doesn't like explain why there's an anomaly there, but there's some physical like insights that we can plot against TimeGPT to try to get that explanation.
Great, thanks. Just taking a look. So apart from anomalies and historical forecast, what other use cases does TimeGPT have API calls for? Are you familiar with that, or should that be a question for Azul later?
That should be a question for Azul, but yeah, like there was also a question if it can do classification. This is basically at the moment a regression problem. So yeah, it's basically trying to do a regression for time series and doing anomaly detection as far as I know. But yeah, we can definitely ask Azul to give us more details.
Yeah, absolutely. There's a couple more questions. Sada says, I would like to validate the effectiveness on my data, but the API key makes it doubtful about the authenticity. I think Sada was also asking if the code is open or closed. And Camilo, you did address this a little bit earlier. Right now, this is only an API, right?
Yep. Yeah.
So, hopefully we'll be keeping an eye on it as well to see if it, becomes open source and you can use it a little bit more securely locally with your own data. But right now it is only an API.
Mm-hmm. Mm-hmm.
All right, going over to some other things. So here's a question from Narhari. Have you compared TimeGPT and other neural network-based models with state SPCE time series, which is based on Kalman filters?
Okay, so yeah, great question. Yeah, Kalman filters are like, they're still very relevant. They were used like in the 60s to actually like in the Apollo missions, because they're very compute efficient. I haven't used them against TimeGPT, but yeah, I assume TimeGPT is going to work a little bit better than Kalman filters, because yeah, Kalman filters are very efficient, but they're starting to age. So yeah, I haven't done a specific benchmark, but I assume TimeGPT is going to be better.
Great. Great. Okay, I'm kind of just picking and choosing. Let's maybe do 3 more questions, and then we'll try to wrap up. Trying to think about the best questions for you. We have huge time series data sets spanning terabytes. So Isha's asking this. Will the data need to be subsetted or partitioned, or can the libraries handle large data sets?
Yes. So most of these libraries, specifically Neural Forecast, has like this Ray backend to handle like distributed computing. So yeah, you could actually use Neural Forecast with big, huge data sets. But yeah, ideally, what we would do is just like a very like MVP with a smaller data set, like what we just did with a single vessel. But yeah, what we're going to do, for example, for the large maritime model, is going to be like terabytes of data. And we actually need like a cluster of compute of GPU, a GPU cluster to handle all of this.
Great. There's been a couple questions about explainability in time series forecasting. I think there was 1 or 2 that was more general, and then one about TimeGPT specifically. Do you want to comment on that?
Okay, yeah, there's, and time series forecasting. Yeah, and actually for TFT, like the idea of TFT is that it's very explainable, and yeah, and hits also like very explainable. So yeah, let's go to TFT. We can actually have a bunch of explainability on the multi-head attention. So what multi-head attention does, it just tells the model what time step it needs to focus on. So here we're gonna know, like, if we have a prediction that seems weird, we can look into the attention like scores and see why, like what it's attending to and why it's giving like those weird values. And for hits and bits, like we can actually get the I don't know, like the trend and the seasonality, and we can have explainability in that sense. We can see like if it's like if it's giving a high prediction, it could be because the season is very high, not the trend. So we can get explainability in that sense.
Okay, great. Here's one rather quick question. Which of the models that you discussed required GPU?
Okay, so that's a great question. Most of them did, like to train. This was a very small data set. We could be trained with CPU, but yeah, most of them require GPU for the training. And for the inference, it could be done on CPU, but at least TimeGPT has GPU inference. But most of them need GPU for training, CPU for inference, except TimeGPT that needs GPU for both.
All right, great. All right, let's do one last question from GA. Can you describe forecasting many time series at once in a tabular format?
Okay, so yeah, great question. Like what we could have is a lot of different variables. So for example, not only latitude, longitude, we can also have like weather variables. We can have the wind speed, the wave height, the current speed. All of those could feed into our model, and all of those, depending on the type of variable, could be like a past covariate or a future covariate. And then we're gonna have like the output could be the lat and long, but we can feed all those time series at once. And then the model, depending on the architecture we build, we could have like a dense layer at the end that can predict both lat and long at the same time.
Great. All right. I think that we'll try to wrap up there. Thank you all so much for coming. We really appreciate your time and your participation and your questions. There were a few questions that were about TimeGPT specifically. I'll be sending those over to Azul later today, and she'll try to answer some of them via email, and then I'll send that out hopefully tomorrow. If not tomorrow, it will be Wednesday. Thank you all so much, Camilo. Thank you so much. Have a great rest of your Monday, everybody, and we will see you soon. Definitely take a look at the Fourth Brain page. We have a couple of workshops coming up. Starting next Friday, we have a one-day workshop on fine-tuning LLMs. In a couple of weeks, we have a longer workshop on building with LLMs. So definitely check those out. And we hope to see some of you in one of our upcoming workshops. Have a great afternoon, everybody.
See you, everyone.